Hello everyone, I would like to present a work titled Stochastic Games with Stopping States and the Application to Adversarial Motion Planning Problems. My name is Sandeep Banik and I'm a PhD student. Both me and my advisor, Dr. Shaunak D. Bopardikar, are from Michigan State University. Significant rise in autonomous systems in multiple areas such as connected autonomous vehicles and smart buildings. In the future, we expect to see a heterogeneous team of robots. All the agents operate in a shared environment. In such scenarios, an agent must determine if the neighboring agents might act adversarially. These agents are generally power or energy limited and must decide to balance between monitoring for suspicious activities and performing the assigned task. In this work, we reason about the mobility and safety or security cost of an ego vehicle in the presence of a non-ego vehicle. We assume an ego vehicle is equipped with sensors such as LiDAR or radar or other sensors generally found in autonomous vehicles for predicting the path of neighboring vehicles for a finite horizon. We develop a framework to reason about such probable adversarial intents of non-ego vehicles, that is, as opposed to deterministic adversaries, we assume stochastic adversaries. Consider a finite horizon decision-making problem between an ego and a probable adversarial non-ego vehicle. The horizon length is given by k. For this illustration, we consider the car on the left in light yellow as the ego vehicle and the taxi as the non-ego vehicle. The adversarial intent of the non-ego vehicle is governed by the parameter rho, that is the probability with which a non-ego vehicle will act adversarially. The decision-making problem at any time instant k is defined by two matrices, Sk and Rk, representing the payoff in the presence and absence of adversary, respectively. The rows correspond to the actions taken by the ego vehicle and the columns correspond to the non-ego vehicle actions. A stopping state is reached when both the ego vehicle and the adversarial non-ego vehicle defend and attack respectively. Once a stopping state is reached, the ego vehicle is aware of an adversary present in the system. The objective function for this problem consists of three terms. The first is the adversarial stage cost. The next is the cost associated in the absence of an adversary. Finally, we have the cost from the stopping state till the last stage of the game. We aim to find the adversary and defender policy over the horizon k, that is, what actions must the defender and adversary take at each stage of the game. The pair of policies are in Nash equilibria when the following inequality is satisfied. In this work, we limit the number of actions to two, that is, a defend and a no defend for the ego vehicle. Similarly, we have an attack and no attack for the non-ego vehicle. We visualize the game tree starting with the value of the game at time 0 given by v0. If an adversarial intent is ascertained, the game is expanded with the pairs of actions corresponding to different stages of the game. Notice a stopping state SS is reached when a defense and attack action are used simultaneously. When an adversarial intent is established, the solution of the game depends on the value under a deterministic adversary, that is with rho set to 1. Under the absence of an adversarial intent, or where the intent is uncertain, only ego vehicle has the set of actions, as the non-ego vehicle defaults to no attack. The challenge is to solve the game simultaneously with and without an adversarial presence. We solve the SSG using backward recursion with a condition for switching between pure and mixed policy. In here, we demonstrate the use of such a framework. We consider a car following or cruise control highway scenario. A non-ego vehicle might act adversarially, that is, to brake and cause the safety distance between the ego and non-ego vehicles to reduce. The ego vehicle has to balance between maintaining a safe distance while also trying to reach its destination. We assume here that the actions of the ego and the non-ego vehicle correspond to braking and traveling at constant predefined speeds. We carried out the experiments using Turtlebot 3 burgers represented as the ego vehicle termed as autonomous vehicle or AV and the non-ego vehicles as the taxi. Here the video shows a car following scenario for a limited time and distance. The plot on the right is a sample from one of the experiments. The AV and the taxi brake according to the policy obtained by solving the SSG. Similarly, we carry out a dynamic stage cost evaluation and experiment corresponding to a lane merging scenario. The ego vehicle has some prediction mechanism to predict the trajectory of the non-ego vehicles, and we reason about the deviations of such trajectory which might be dangerous. We use turtle burgers again, represented as the autonomous vehicle or ego vehicle, and taxi or the non-ego vehicle. Similar to the cruise control, we assume the actions of both the ego and the non-ego vehicles to brake or use predefined speeds. This video shows a sample experiments with a forward trajectory followed by a lane change maneuver. We notice that the ego vehicle slows down when the taxi tries to merge in. The plot on the right shows a sample policy. The plot shows the probability of braking by both the AV and the taxi, and we observe initial and later braking by the AV. The taxi, on the other hand, does not brake during a lane change and might potentially brake, acting like an adversary at a later stage. The main challenges in this work was the incorporation of a probable adversary as opposed to a deterministic adversary, the balance between performance and safety or security, and solving the zero-sum game over the finite horizon with stopping states. The contributions include modeling of such a task with a stochastic adversarial intent and developing closed-form solutions and analyzing the same. Future directions include non-zero sum formulation and larger action space. Although this work is demonstrated between an ego and a non-ego vehicle with the appropriate choice of stage cost matrices, a variety of systems can be incorporated in the SSG framework. This brings us to the end of the presentation. I hope everyone enjoyed it. Please refer to the paper for more details. Thank you, and you can post your questions in the comments.